For centuries, the logic of auctions has relied on a single point of authority. An auctioneer controls the inventory, manages the pace, and serves as the strict, centralized source of truth for every bid placed in the room. When you move that model to a digital peer-to-peer marketplace, that single point of control disappears. You are suddenly managing millions of concurrent users competing across an entirely unmanaged catalog, all requiring real-time validation. To operate at a global scale, the platform has to meet strict service-level agreements. It must support 10 million active listings and handle 50,000 peak bids per second. It has to keep bid processing latency under 200 milliseconds, and it must do all of this while maintaining strong data consistency. In standard retail, inventory is static until a user adds it to their cart, but here you cannot put an item in a cart. The price and the identity of the highest bidder are constantly mutating based on concurrent global inputs. In a second price proxy auction, where the winner pays just above the second highest bid, participants use an economic strategy called sniping. Bidders intentionally hold their offers until the final seconds to hide their true valuations and prevent premature price escalation. This is a historical bid log from a real auction platform. You can see how multiple distinct bids cluster intensely in the final minutes and seconds before the deadline. This chart maps elapsed auction time on the x-axis against bid volume on the y-axis. The data shows a near-total absence of activity for the majority of the timeline, culminating in a massive exponential spike in the final 1% of the auction window. That exponential spike translates into severe database contention. At the moment of closing, the system must process upwards of 500 requests per second, with every single transaction attempting to mutate the exact same row of data simultaneously. Human economic strategy directly dictates database load. This localized data contention breaks standard relational database designs. The initial impulse for most engineers is to rely on a standard relational database, storing the current highest bid directly on the auction record to enable fast reads and avoid expensive table scans. And because network latency makes client-side timestamps completely unreliable, the system has to assign strict server-side timestamps to determine exactly who bid first. If you try to process these bids using pessimistic locking, the database locks the row to prevent race conditions. Concurrent threads begin stacking up in a queue. Within milliseconds, database connection pools exhaust, and transactions time out before the auction even ends. Switching to optimistic concurrency control simply inverts the failure. 500 threads read the same initial state. The first to write succeeds, and the other 499 bounce off, generating a massive retry storm that completely overloads the API. Concurrent processing paradigms collapse under localized auction contention. To survive, the architecture must force sequential execution. The solution is an ingestion-to-execution pipeline that serializes the data long before it touches a persistent disk. Incoming bids are routed through an API gateway and into an event streaming platform. By keying the message broker partitions to a matching auction ID, the system guarantees that all transactions for a specific listing arrive in strict sequential order. These strictly ordered partitions bypass disk storage, feeding packets directly into an in-memory execution engine. Inside, a single-threaded loop executes an atomic Lua script. It swallows incoming packets, validates the bid increment against current state, and outputs a confirmed update instantly. By moving the validation logic to a single-threaded in-memory loop, the system eliminates race conditions entirely. It bypasses distributed locks and easily clears the 50,000 bids per second requirement. There is a specific edge case that threatens this high-throughput pipeline: competing proxy bots. If two users set automatic maximum budgets, they could trigger an infinite performance-draining loop of minimum bid increments until one taps out. To resolve this instantly, the Lua script utilizes a jump-to-price algorithm. Instead of looping through endless micro-increments, the script calculates the exact intersection of both budgets and jumps straight to the mathematical ceiling of the lower maximum. By resolving these competing maximums in a single atomic memory write, the platform prevents proxy wars from degrading the main execution loop. The write path is heavily protected, but the read path presents a completely different engineering challenge. Writes require strong consistency, but the visual auction countdown viewed by users can tolerate roughly 500 milliseconds of eventual consistency. As the in-memory database confirms a bid, it immediately publishes a lightweight notification event to a pub subchannel. This event hits stateless WebSocket gateway pods. They multiply the signal, pushing the updated price down to thousands of client browsers watching the auction. The initial bid validation acts as a trigger, creating a cascading wave of real-time updates that illuminate millions of endpoints globally, almost instantly. Isolating strongly consistent writes from eventually consistent reads is what allows the platform to scale its viewing audience infinitely, all without applying a single ounce of pressure to the critical bid execution path. When the auction clock reaches 0, the system has to migrate the final winning bid out of the temporary in-memory cache and write it into the persistent relational database. To prevent duplicate processing during this transition, the system uses the fencing token pattern. A dedicated settlement worker generates a unique sequential token, processes the final result, and stamps the database with the verified state. If a settlement worker crashes before committing a write, the system spins up a new worker with a newer token to complete it. When the original zombie worker wakes up and tries committing with its outdated token, the database actively rejects the payload. This specific pattern guarantees effectively once processing, protecting the persistent database from corruption and duplicate updates, even when distributed infrastructure fails. Once the winner is recorded, post-auction settlement begins. This spans multiple independent domain boundaries: billing, inventory, and shipping, which cannot be locked simultaneously without grinding the entire platform to a halt. Using the Saga pattern, a centralized orchestrator issues sequential transactions, authorizing the card, reserving the item, and generating a shipping label. If a downstream service fails, like fulfillment, the orchestrator instantly reverses direction, firing compensating tasks backward to release inventory and refund the payment. Building a global auction engine requires strict isolation of state mechanics. You serialize writes in memory, you decouple and fan out your reads, and use Saga orchestration for settlement. That is how you solve the bottleneck.